This is problem 2 from chapter 13. The two boxcars A and B have a weight of 20,000 pounds and 30,000 pounds respectively. If they are freely coasting down the incline when the brakes are applied to all the wheels of car A, determine the force in the coupling C between the two cars. The coefficient of kinetic friction between the wheels of A and the tracks is 0.5. The wheels of car B are free to roll. So we have kinetic friction on the wheels of car A only. We're going to neglect the mass of the wheels in this calculation. So I left them out of my picture there. And they say suggestions solve the problem by representing single resultant normal forces acting on A and B respectively. Okay, so I'm going to do a free body diagram for A and a free body diagram for B, and we are looking for the force in coupling C. So let's call that F sub C. Okay, so for a problem from chapter 13, our basic procedure is going to be first to draw the free body diagram. In this case, we're doing free body diagrams for two different objects. And the first question you can ask yourself is there a force of gravity acting on the object? And yes, in this case there is. And that force is 20,000 pounds for car A and 30,000 pounds for car B, although I think for the sake of space, I'm just going to write that as FGA and FGB, but those do have known values. Okay, after you put the force of gravity on your free body diagram, you can ask yourself, what else is touching the object? Well, the track is touching the wheels, or you could say the car, since we're ignoring the wheels in this case. And on car A, we have a normal force, which is called the normal force because it's perpendicular to the surface of contact. And the track also exerts a force which is parallel to the surface of contact, and that is the frictional force. So let's call that FKF. And we do not have a frictional force acting on car B, so I don't need to put a subscript A on there. What else is touching car A? Well, coupling C is touching car A, so we have the force from C, and that's it. So now we can move on to car B, and we also have the force of C acting on B, and we have a normal force, which is perpendicular to the surface, and there's no frictional force, so that's it. Now, if you were to look at the whole system of A and B and coupling C together, then these forces should cancel out because that's an internal force. So they have the same magnitude in the opposite direction, and thus they do cancel out. So now that I've done my free body diagram, the next thing that I want to do is actually draw another free body diagram, although if you want to put everything on the same free body diagram, you can, but I like to do another free body diagram with all of the forces broken up into components, so it makes it easier when I go to use Newton's second law. So we have a 5-degree angle here, and I have to give my coordinate system. So I'm going to say that this is the x direction and this is the y direction, and I have a 5-degree angle here. Oh, when you choose your coordinate system, usually what you want to do is to choose your coordinate system such that the acceleration is just in one direction. So it just has one component. In this case, that would be an x component. So we're choosing our coordinate system such that the acceleration in the y direction is equal to 0, which is going to make it easier to solve the equations. Although if you wanted to use a coordinate system where x was horizontal and y was vertical, you could still solve the problem that way. It would just mean that the math that you're going to have to do is more complicated. So I would just have to break the force of gravity down into components. I did this in a previous problem. I'm not going to do it every time. But if you have your force of gravity acting straight downward like this, and you have your angle of 5 degrees here, then this angle here is 90 minus 5 degrees because this is a right triangle. And so if we do a right angle here, this angle is going to be 5 degrees, which means when you break the force of gravity down into components, this component, because that's adjacent to the angle, is going to be the cosine component. So this is FGA cosine of 5 degrees, and this is FGB cosine of 5 degrees, and then we have a component going this way, which is the sine component. Okay, and then all the other forces are either pointing only in the y direction or only in the x direction. So the force of gravity was the only force that I had to break down into components. So I'm just going to write all my other forces on here. Okay, so now that I've done that, I can look at Newton's second law. I'm going to do this in the x direction and also in the y direction. I'm going to do this for A, and I'm also going to do this for B. So usually it's helpful to start off looking in the y direction first, because if you have a force of friction acting in the x direction, it's helpful to know what the normal force is so that you can calculate the force of friction. Although, if you sum up the forces in the y direction for car B, that's equal to the mass times the acceleration in the y direction, which is just equal to 0. That's going to give you the normal force for B is equal to FGB, which we know, times cosine of 5 degrees. So we could figure out what that is, but it doesn't really help us because it just gives us the normal force on car B, which if you're interested in knowing what it is, that's how you find it. But if you're only interested in finding the force of C, it doesn't really help because there's no force of friction for which you have to use this normal force. So that didn't really get us anywhere, but it was pretty easy to do, so it doesn't hurt to start with that. For object A, the sum of the forces in the y direction is equal to 0 because the acceleration in the y direction is equal to 0. And I have the normal force going in the positive y direction, so that is equal to the force going in the negative y direction. FGA is 20,000 pounds, so it's 20,000 pounds times cosine of 5 degrees, which is 19,924 pounds. Okay, so now moving on, I can look at the sum of the forces in the x direction. That's equal to the mass times the acceleration in the x direction. And it is important to note that these cars are moving together with the same acceleration. So this is mass A, this is mass B, that's mass B also. But the acceleration is the same. So looking at car A first, we have going in the positive x direction, the force of kinetic friction. So that's FKF minus force C minus FGA, which is 20,000 pounds, times sine of 5 degrees is equal to the mass times the acceleration in the x direction. Well, we weren't given the mass, we were given the weight, but we can find the mass. I'll just do this off to the side. Because I know the weight is equal to the mass times little g. So the mass is equal to 20,000 pounds divided by 32.2, which is 621.1. So that's the mass times the acceleration in the x direction. I can use the normal force that I have here to find the force of kinetic friction. So the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. So let's put that in. The coefficient of kinetic friction is 0.5. The normal force is 19,924. Then I have minus FC. 20,000 times sine of 5 degrees is 1,743. And let's combine this 0.5 times 19,924 with the negative 1,743, and that gives us 8,219 minus FC is equal to 621.1 times AX. Okay, and now we're going to leave that there. We have one equation with two unknowns, and now we're going to look at B, sum up the forces in the x direction. We only have two forces acting in the x direction, so we have FC, which is going in the positive x direction, minus the force of gravity for B, which is 30,000 times sine of 5 degrees is equal to the mass of B, which is 30,000 divided by 32.2 times the acceleration in the x direction. 30,000 times sine of 5 degrees is 2,615. So this is minus 2,615, and 30,000 divided by 32.2 is 931.7. Now we have two equations and two unknowns. So I can now solve these two equations, and what I'm looking for is force C, which means I can solve this equation for AX, plug it into this equation here, and find force C. Or if you want to find the acceleration, you could solve this for force C, put that in there, find the acceleration, and then use either one of those equations to find FC. So, I mean, I would kind of be interested to know what the acceleration is, but they're not asking us for that. So let's instead just, I guess, take this equation here and divide by 931.7. That gives us an equation for the acceleration in the x direction, and then we'll just take that and put it in here. So we get 8,219 minus force C is equal to 621.1 times FC minus 2,615 divided by 931.7. Okay, from this point on you should be able to solve it on your own, and you are free to do that. If you want to see the rest of the solution, we can take 621.1 and divide it by 931.7, and that gives us 0.6666. If we distribute that, we get 0.6666 times FC, and when I multiply that by 2,615, I get 1,743. And then let's bring this FC over to this side and the 1,743 over to the other side. So that's 8,219 plus 1,743. When I bring the FC over here, it becomes positive. If I add that to the 0.66666 FC, I get FC times 1.6666. And then finally, I have FC is equal to 8,219 plus 1,743 divided by 1.6666, and that gives me 5,977. Depending on how you solve it, after you get two equations, two unknowns, you may get 5,978. Maybe we should round it to three significant figures. Maybe we will. So to three significant figures, this is 5,980, and the units are pounds. And that concludes problem 2.